Success Insight shares the stories of the people with passion and drive who make things happen in the world. Here's your host, Howard Fox.
Hello, everybody. This is Howard Fox, and welcome to another episode of the Success Insight podcast. Our guest today is Tom Dillinger. Tom is an accomplished electrical engineer and the author of VLSI Design Methodology Development. And before I go any further, I want to tell everybody I have done my homework and I now know what VLSI stands for, but we'll get into that when we actually talk to Tom. Tom is an authority in microprocessor design. Tom carefully introduces core concepts and guides engineers through the modeling, functional design, validation, design implementation, electrical analysis, and release to manufacturing of microchips. This guide is for all VLSI system designers, senior undergraduate or graduate students of microelectronics design, and companies offering internal courses for their engineers at all levels. It is applicable to engineering teams undertaking new projects and migrating existing designs to new technologies. Why, you may ask, am I having a podcast about this topic? Well, we are now officially within the month of December between the new year and we just finished Thanksgiving. This is the time of the year when everybody's buying things for their family and friends, and electronics are in that list of things. And who better than to talk to Tom Dillinger about his work and his book. Tom, welcome to the Success Insight podcast.
Thank you, Howard, very much.
So I actually remember having this conversation of when you and I first chatted about your book, VLSI Design Methodology Development. And I remember thinking to myself in sharing, this is a perfect opportunity because we're in the holidays. Almost everything we touch, I should say, has electronics in it and microprocessing chips. And I just think it's an amazing in the development and the technology that is on the end of a hair follicle. Tell us a little bit more about yourself and what prompted you to want to write a very substantive book like this.
Well, thanks, Howard. You are correct. The influence of microelectronics has just become increasingly pervasive throughout all facets of our life, from basically consumer products that we're all seeing in this holiday season, but also extending substantially into automotive products. The amount of microelectronic chip designs in new automobiles, as far as their safety systems and automated or assisted driving systems, has certainly increased. Medical technology is certainly embracing microelectronics to a much greater degree. You're right, microelectronics has become pervasive. It's really been an exciting field for me to be in over the past 30 years in terms of just the continued technological advances that I have witnessed. They are truly amazing. As you alluded to, we are now able to routinely manufacture transistors that are of a dimension roughly 1,000th the diameter of a human hair, and 10,000 transistors in the diameter of a human hair is certainly within sight very soon. That ongoing technological advancement has been pretty amazing, pretty exciting to be a part of.
I am curious, as you began your career, just for a second, looking back of what you have witnessed now, what you're experiencing, what you're teaching new engineers, students through your book, what do you say to all the advances in the 30 years of your career from when you started? If you were to kind of give a look back, what kind of insight would you have?
Well, that's a great question. The one constant that has been pretty pervasive throughout these advances in microelectronics has been the ability to manage complexity. The amount of functionality that is being included now on a silicon microchip the size of your fingernail has continued to increase with the transistor scaling that we alluded to just a minute ago. As a result, with so much functionality that is being added each generation to a microelectronic chip design, managing the complexity of that functionality has always been a pervasive challenge, and therefore something exciting for an engineering student to address. How do I take a large, complex system design that could go in any of a number of different applications and divide that large system into more manageable subsystems that I can design and verify efficiently before integrating them together?
Interesting. And so the microchip, is how old?
Wow. Well, the first microchips really evolved in the late 1960s, early 1970s timeframe, with frankly only a very limited number of transistors able to be fabricated on a chip design. Over the past 50 plus years, we have continued to see tremendous technology improvements. We've gone from a dozen transistors on a chip design 50 years ago to over 20 billion transistors on a chip design today.
That is an amazing number, which now brings me to the acronym VLSI. What does that stand for?
VLSI stands for Very Large Scale Integration. There have been really a succession of generations of complexity that have been categorized as sort of small scale integration. That's the few transistors per chip design we talked about many, many years ago, through more of a medium and large scale integration. Today, the complexity of the systems that are being designed for a silicon microchip, we're calling very large scale integration of the billions of transistors.
That is amazing. And a question that I have is, you've used the term generations a couple times now. How many generations? That's not probably the right question.
No, it's a perfect question.
Okay, go for it.
The evolution of the complexity of what we're able to integrate on a single silicon microchip is truly dependent. The designers and the manufacturing resources are closely interdependent and intertwined. So your question's a great one. The manufacturing of silicon integrated circuits, microchips, has gone through a succession of manufacturing generations that have enabled designers to put more transistors on a silicon chip. So yes, we talk about multiple manufacturing generations that have allowed us to shrink and scale the transistors and the wires that are present on each chip design. We tend to refer to those manufacturing generations by the transistor dimension, the minimum size transistor that can be manufactured using the technology that's available at that time. Currently, we are talking about manufacturing transistors that are 5 nanometers in size. So design engineers, electronic engineers will routinely refer to today's technologies as a 5 nanometer transistor technology. But over the past 50 years, there's probably been roughly 20 of these progressions of transistor scaling using very, very advanced photo imaging and etching equipment that has been fundamental to allowing us to build these more complex designs.
Would it be safe to say that the size of these chips going from a 5 nanometer chip is we can continue to place more circuitry, for the sake of a better word, onto the chip, as long as the equipment that is actually doing the production I would imagine that has to keep up with what's going on the chip. I mean, you have to continually have improvements in the equipment that's going to build the chip. Is that safe to say is true?
Oh, Howard, you nailed it. We're at kind of an interesting inflection point in the design of electronic systems. The advances in equipment have truly been amazing, but correspondingly, the cost of that capital equipment has been a pretty significant investment. And candidly, the number of manufacturers that are able to sustain that financial investment has been dwindling. There's likely only going to be a relatively small number of companies that are able to manufacture, at least today, manufacture transistors of that small a dimension. So yes, we're certainly driven to integrate more functionality together for the performance benefits and the functionality, but the costs are starting to creep up a little bit to achieve that integration. So engineers and the electronics manufacturers are taking kind of a new approach to try to address some of the cost pressures to continue to drive this integration. We are now routinely putting multiple silicon chips into a single package. So rather than trying to integrate more and more functionality on a single piece of silicon, which is still has performance benefits. Integration translates to performance, but the costs, that's an interesting trade-off. Some electronics manufacturers are saying, I will take two chip designs, smaller chip designs, one could even be in an older technology, and put them together in the same package and provide more functionality at a more attractive price point. And you're seeing that in a broad range of products. Today's consumer phones specifically are kind of driving the packaging technology market to put multiple pieces of silicon, multiple silicon chips together in a single package.
Interesting. So the manufacturers are making the call that the cost benefit, or there's a diminishing return of trying to pack more capacity and capability into a single chip. We can accomplish the same thing by integrating two or more chips together. Did I hear that correctly?
You hit the nail right on the head. One area that this has been particularly attractive, I'm sure your listeners are aware of, many computer products require a significant amount of memory to store programs, to store data that their programs operate on. And they're maybe familiar with the fact that memory is often, or at least traditionally, has been provided separately from the microprocessor or the engine, if you will, of their electronic products. With these advances in packaging, we are seeing lots of companies taking the memory chip designs out of their traditional packaging and putting them together with the microprocessor into a single package and bringing some amount of memory closer to the processing engine has provided significant performance and cost advantages.
That is interesting. And if I'm thinking through this correctly, when you and I are about the same age. I grew up with both the Windows and the Apple computer. It was a floppy drive. I guess it was like 5.5 or 5.25. I forget. Then it went to the smaller disk, 3.5, 3.25. Again, I forget. Then there was the CD. Now the flash drive. And so what I think I'm hearing you say is eventually we're not even going to need the flash drive anymore. All that memory is going to be within the construction of the computer itself.
Well, some amount of that flash memory, or have you ever opened up your PC and put what's called a memory stick in it to add more memory to the motherboard? Some fraction of that memory, whether it's flash, which is permanent storage, or the dynamic memory that you can buy today on a memory stick, certainly some percentage of that memory, we are seeing a significant trend to packaging that together with the processing engine. It won't be all, but there will be, if you will, kind of a hierarchy of memory. Some amount very fast, very close to the processing engine, and then the balance of the memory storage still using kind of the separate packaging and traditional method. But we are seeing some pretty exciting system designs that are pulling memory in much closer to the processing engine.
Wow, it's amazing. And let's go back, if we can, to the book VLSI Design Methodology Development. I mean, this is a pretty substantive book, Tom. I mean, for our listeners, you're going to go out to the Amazon page. We'll provide you a link to it. 750 some pages. This is not a insignificant book. And what prompted you to want to, or why did you feel there was the need to produce this kind of a book? What were you trying to solve something, or was just a labor of love of 30 years of doing this kind of work? What was the reason behind it?
A little bit of both.
Okay.
Yes, it truly was a labor of love, but the problem to solve is that technology, as we alluded to, has moved so quickly that it's been rather difficult for universities to keep up. Some of the textbooks that are currently used in microelectronics courses are 15 years old or older. And that, as we alluded to, that's several manufacturing generations behind what graduating electrical engineering students are going to be faced with today. So the problem to solve was to try to refresh or bring students, expose them to design methods, which are getting more complex, to kind of bring them up to a more current level so that they can hit the ground running. The size of the book, I tried to address the complexity of the design and verification and manufacturing tasks associated with today's technologies. Hopefully, students will find that current or that updated treatment of interest.
This is definitely a book for a university student, whether it's undergraduate or a graduate student. Is this to a company? They've decided to go into engineering school, and I suppose you have to learn the basics, and you kind of gradually work your way up in the classwork and then the homework and studies with more complex concepts and ideas. And is this book then designed to take what is kind of they've reached a point of, here's everything the school is teaching me. Now this book is basically the future of engineering, this type of design?
I think that's a good description. Students certainly still need the basics, but technology continues to march on. And even professional engineers in their career, they may benefit as well from a introduction to very leading edge, very current technology issues that microelectronics designers and electronic product manufacturers are facing.
So in addition to students and professional engineers, these engineers could be any other manufacturer, or could be a company that has engineers on staff who need to understand this complexity in order to help solve a problem. Would that be safe to say?
I think that's right on.
By the way, I got to tell you, Tom, you've said I've been spot on a lot of times today. You were scaring me because I was not a science guy, okay? I was more in the head with psychology. So you're scaring me, by the way. So please go ahead.
Oh, no, your questions, Howard, are truly spot on. I'll give you an example where maybe a practicing engineer might find some of the material of interest. One of the areas that I tried to emphasize that students, college students certainly don't get much exposure to, and increasingly professional engineers are maybe not aware of, is the importance of reliability of your electronic design. And by reliability, I mean it's continuing to function at performance throughout its lifetime. One of the areas we talked about kind of at the beginning is the increasing amount of electronics that is being incorporated into new automotive designs. You turn on the TV, you see all the advertisements for the new safety features that are being integrated into current electronics modules inside cars. And there's certainly plans for much more autonomous driving and more sensors and electronics in cars. The reliability of those electronics has to be premium. It has to last over a very extended lifetime, much longer certainly than the lifetime of today's smartphones, as an example. And it also has to be functional in the automotive environment, where if that electronics is under the hood, it's going to be exposed to much more severe temperature extremes than would a smartphone or other consumer product. So all engineers need to be cognizant of what are the lifetime reliability requirements of their design and what environments will their designs be operating in, automotive one being a very challenging one. So there's a whole section of the text dedicated to how to design and analyze the reliability of my circuits over an extended lifetime.
Just coming back from my hometown in Detroit, I took Southwest Airlines, and it's probably my favorite airline. And it amazes me the process of taking off and landing the airplane. And we actually had a guest on not too long ago, Dan Pegram, who's a retired Air Force pilot and also retired from Southwest. He wrote a children's book. And the idea of this airplane, and I know it's physics which allow the airplane to take off because of the curvature of the wing and the airspeed. But at the end of the day, it's electronics that are turning that engine and keeping that engine going within lots of very extreme conditions. And so as you were describing this, with the cars and anything that has extreme usage requirements. So the airplanes, the cars, this whole technology has to be just spot on. And the ability and the capacity of people to learn and develop and advance the capabilities of these chips is just truly amazing. So hats off to you all, because I mean, my car is 20 some years old. I probably do need a new car, but it's stuff that's just finally starting to wear out. But in the days of microchips that we have today, things, they're designed to work and work. They're just everywhere. And all of them have various tolerances, I guess, depending on the need for which they're going to be used. Where do you see the future of microprocessor design going? I mean, we're getting into artificial intelligence now. That's the big word in a variety of professions. But where do you see this technology going in its use? Do you have any inkling for that?
Oh, what a great question, Howard.
You did it again, Tom. You said it again. I'm going to be patting myself on the back after this.
Let's take artificial intelligence and machine learning as an example. And you're correct. It is a very, I'll say, hot and growing segment of the electronics industry. We are probably just at the beginning of finding interesting and important applications of machine learning. Today, we're familiar with the voice recognition from your personal assistant or the face recognition that your social media site highlights, hey, I found a picture of a friend. We're truly just at the beginning, I believe, of finding applications for those kinds of algorithms. To make those algorithms as efficient as possible requires an electronic design that's a little different from the traditional big microprocessor and memory running a traditional program. So kind of a long way of saying, as more and more electronics is integrated, either in a single chip, cost effectively, hopefully, or multiple chips together in a single package, I think what you're going to find is less and less dependence upon a traditional microprocessor. And today, microprocessors are really more than just a single engine. Today's microprocessors include multiple, we call them cores, computing cores that allow you to run multiple programs concurrently, but they're pretty much homogeneous cores. If you go shop for a laptop or a new personal computer, no doubt you'll see its processor is described in terms of the number of cores that it contains, meaning the number of concurrent program threads it can execute. I think what you'll see in the future with applications like machine learning is electronic designers will have to become more application specific, meaning I can't just put more of the same processor core together on a silicon chip. I need to judiciously find what is a good combination of optimal electronic circuits for very unique applications like machine learning. So much more diversity in electronic systems design than perhaps we have today. And one other thing that will certainly continue to be important, we haven't talked yet about power dissipation. With the ability to put 20,000 transistors on a single chip design, if they are all active concurrently, that dissipates a lot of electrical energy. Today's chip designs, the highest performance microprocessor chip designs can easily dissipate more than 200 watts. We are all familiar with some of the power savings techniques that are being used in our consumer products today. I think you're going to see a much greater emphasis on how can I efficiently add more applications, add more system functionality, but also be very cognizant of the power that consumes. So there'll be more techniques for switching on and off different parts of your system design on an as needed or on demand basis.
Wow, that is amazing. That is amazing. Tom, in the time we have left, and as I shared, this is going to go by very fast. And I think we've covered a lot of material here. What would you like to share with the consumers of this book that we haven't alluded to in our discussions today? For people like me, these chips are continuing to change my life. And I look at it in a very tunnel vision fashion. I expect my computer to get turned on. I expect to run my programs. I expect my smartphone to work, et cetera, my car to start and run seamlessly, take my flights on Southwest Airlines seamlessly. The complexity that you have to deal with and the folks that are going to be designing the chips of the future have to deal with, there's a different concern or there's a different perspective per se. What would you like to share with them about this work and then the advances that are taking place?
Well, at a very high level, Howard, one comment would be never stop learning. The technology continues to advance, and to really leverage the capabilities of these new technologies, it's important to continue to strive to learn and extend your experiences beyond maybe the methods that you have used today to methods that are going to be important tomorrow. One thing we haven't talked about that is pretty critical to enabling these advances in technology is the field of computer-aided design and the tools that engineers use to describe and verify and analyze their microelectronic chip designs. So maybe one area that people that might be looking for a broader exposure that I think they would find in this text is a discussion of how computer-aided design tools and methods are enabling these technical advances. And it's critically important to become aware and familiar with some of these computer-aided tools that are going to be a fundamental part of any engineer's toolbox.
Okay. I'm curious too, with the complexity that the engineers of the future have to look forward to, who are the engineers of the future? Are they here in hometown America? Are the schools, the universities teaching the students what they need? Are we getting people excited and interested that there's a great future for them from a jobs perspective, a career perspective?
What a great question. In the United States, I think it's fair to say electrical engineering is still a very in-demand, very important, well, I should say specifically microelectronics engineering, very important and very good career path for students. But candidly, the investments that are being made to offer more microelectronics education and expand the microelectronics industries, it's really taken off in Asia. Very concrete example, the Chinese government has made it a critical government initiative to enhance their microelectronic design curriculum at universities, their microelectronics manufacturing capabilities. We are going to potentially see a shift in where our electronic systems and products are being designed and manufactured to countries like India, China, Taiwan. Those are countries that have made this a critical area for their investment.
That, I suspect, does not bode well for us.
Potentially.
Tom, what are your final thoughts on our discussion today? I mean, I want to ask you to share the best ways for our listeners to learn more about you and your work, and most certainly to learn about the design methodology development via the book. And I want to share that in just a second. But any final thoughts, I mean, kind of encapsulating our discussion, the work that has gone into this very important book, and what final thoughts?
Well, the electronics industry is an exciting one. It's been a terrific career, and I am continuing to look forward to ongoing technical advances and trying to stay as current as I can. I would encourage others to do the same.
Fantastic. So, Tom, if our listeners would like to learn more about you and your work, where's the best places for them to go?
There is a website for the book. It's www.VLSI Design Methodology, all one word, .com. They can reach out to me through that website or through LinkedIn as well.
Fantastic. So we will most definitely provide links on our show notes to the website, VLSI Design Methodology.com, as well as your LinkedIn profile. For professionals like yourself, myself, LinkedIn is most certainly a place to go to connect with you and to start a conversation. And we'll also provide the backlinks to the book on Amazon. Tom, thank you so much for joining us on the Success Insight podcast today. It was a very interesting conversation.
Howard, it was truly a pleasure.
Who would have figured, folks, that here we are talking about microprocessor design, transistors, artificial intelligence, machine learning, chips, chip packages. This was an interesting conversation, and the big takeaway is everything or nearly everything we touched today has a chip in it or a chip package in it. And I think it bodes well for us who are the consumers to appreciate the level of effort and education and persistence and really the whole design aspect of it, and to be aware of how this work affects who we are today and really what our capabilities are going to be tomorrow and days and years to come. So we hope you enjoyed our conversation today with Tom Dillinger, electrical engineer and author of VLSI Design Methodology Development and an authority on microprocessor design. Again, this is very timely given we are now between the Thanksgiving and the New Year's holiday. So go buy some electronics and be safe wherever you are where electronics are involved. And as we say every show, wherever you are, whatever you're doing, go out there, have a phenomenal day, and we'll see you on the next episode of the Success Insight podcast. Take care now.
Success Insight is a production of Fox Coaching and First Story Strategies. Find us online, successinsightpodcast.com.